Ben bir ders daha alacağım. Bir daha alacağım. İkinci derse girenler için. Ondan sonra bazen her ders toplam alacağız. Tamam mı? Onu kırmayın. Böyle geç geldim otobüstüm falan. Okay, so the monitors are for in order to address the difficulty of employment, difficulty of usage problems of the semaphores and the mutex and the condition variables. And Java directly supports monitor type synchronization methods. The whole methods or the whole code segments can be synchronized using the synchronized keyword. Okay. So we looked at this, and again, as always, we talk about the advantages of the stuff that we learned, and we look at the disadvantages. So what are the disadvantages of monitors? They are nice, but they are language dependent. For example, in C and C++, we don't have that synchronized keyword, okay? So the language doesn't support these type of mechanisms for some of the languages. For newer type of languages, they are okay, but old language doesn't do that. And monitors, semaphores, and mutexes are all fine on a single machine, even on a multiprocessor. That's okay. They work fine, but they are all good for the shared memory location. Okay, so these are monitors, semaphores, mutexes. They are all okay. They are all mutual exclusion of the shared memory locations. Okay, shared memory locations, which is fine for the multi-threaded applications. But if we are using two processes on two different machines or two processes with different address spaces, then monitors, semaphores, and mutexes will not work. Okay, will not work. They don't work well. They don't work without some shared memory. We need shared memory for these to work. So for the other types of communication between the processes, for example, over a local area network or wide area network, whatever on a network, we use some other kind of mechanism for the inter-process communication. So we need these two functions or functions similar to these two send and receive functions. Okay, model based on network operations, send and receive. Okay, so we will do message passing. We will send messages between processes and receive messages between processes. Receiver blocks if there is no data available. We will wait for the producer to produce something. Sender blocks if the receiver buffers are full. Okay, sender blocks if the receiver cannot receive what you are sending. Okay, so send and receive mechanism is the solution for this shared memory location. So if you are addressing this shared memory location problem, if you are addressing the shared memory location problem using this send and receive functions, why don't we use them all the time? Okay, if send and receive solves all these problems, why don't we use send and receive all the time instead of using semaphore and mutexes and the monitors?
Performance issues maybe.
Performance issues, exactly. I mean, send and receive, it uses the network connections even on the same machine. They are all kernel calls. You need to switch to kernel space. They are very, very slow. So if you are on the same machine, if you are using the same address space, then you should definitely use monitors on the semaphores or the mutexes because they are much, much faster. Most of the time, most of the implementations, they don't go into the kernel mode, kernel space at all. Everything is handled in the user space, so they are very, very efficient. They are very, very fast. But if you are on different machines, then you need to get help from the operating system and use send and receive. There are many complex issues with the networks, like the acknowledgement. If you, for example, if you send something over the network, how do you know that your message is received by the receiver? Okay, so for that case, sometimes receiver sends you an acknowledgement signal, but the acknowledgement signal might get lost. So you might send the same thing twice, and that means that the consumer receives the same produced item more than once, sometimes 0 times. The messages might get received out of order, and those kind of problems we will not talk about. Those are the problems of networking systems, and they are all out of scope of this course. So we will not talk about those. But I will show you some examples with the send and receive functions using the message passing. Many different paradigms of how to use it. One way is the rendezvous, one message at a time. Sender and receiver operate in a lockstep. It's like a strict alternation. Remember strict alternation? Only one process can use the critical section, and next it's the other process's turn. They take turns in using the critical section. In the rendezvous kind of scenarios, one message at a time, sender and receiver operate in lockstep. Okay, you send it, receiver receives. You send it, receiver receives, and it's a rendezvous kind of lockstep. Okay, turns. The other one is the mailboxes, like the mailboxes, fixed size buffers on channel. Sender blocks if they are full. So it's like a consumer-producer problem with the buffer sizes. Or the explicit requests, empty messages from the consumer to the producer. Consumer sends empty messages, okay, with the buffers to the producer. The producer fills them and sends them back to the consumer. And we will look at an example of this one. Okay, producer-consumer problem with message passing. Okay, so this is my producer code. This n is 100, number of slots in the buffer. Let's look at the consumer code first. It's more interesting. Okay, remember n is 100. I have 2 items and I have a message. Okay, so for 0 to n, send producer m. So it sends n empty messages to the producer. Okay, so we are using this paradigm, explicit requests. Okay. So the consumer sends n empty messages, says the producer to fill in those messages and send me back. So the first thing consumer does here is send n number of empty messages. Okay, and then in an infinite loop, it starts waiting. Okay, it starts waiting. Says that receive an item, and I extract the item. Okay, and I extract the item, and I send the producer again this message, and I consume the item. I receive the item, and I send the producer the same item again, so that the producer can fill in that message and send me another message. And in the meanwhile, I am consuming it. Let's look at the producer side. Producer, it produces an item. Okay, it produces an item. It doesn't send it immediately. Okay, it waits for the consumer to send an empty message. It gets the empty message. Okay, it fills that message with this produced item and sends it. Okay, it's received and sent. It's kind of counterintuitive, but it works that way. Because this is how they explicit requests empty messages from the consumer to the producer, and rest continues that way. Okay? So this is a producer-consumer problem using message passing, much expensive. But if we are not on the same machine, if we are not using the same address space, there is nothing else we can do. We have to do that kind of expensive stuff. And if anything happens when you are receiving something, a network problem, packet loss, out of order packet reception, those are the problems with those problems has to be solved by the networking part of the operating system, which is a very specialized topic left for the computer networks course that you will take in third year or something, I don't know. Okay? Any questions on the producer consumer with the message passing? Let's see if I. Okay. Okay, I didn't miss anything, I guess. So I can continue. No? Okay, I will continue. Another specialized synchronization topic is barriers. Barriers are, I will not go into the details, it's something like that. Let's say I have 4 threads or processes. They are working on different parts of the same data structure. Okay? And at some point of time, I need them to be synchronized. I need them at the same phase. So I put a barrier here. They run up to this barrier. When they reach, all of them reach, I will let them continue. Okay? I will let them continue. This is called barriers. And it is used most of the time for scientific computations. The book has a very good example on it. Let's say I have a special two-dimensional plate, okay? Two-dimensional plate. Let's say in this plate, let's say this is a copper plate, and this is a cold air, and this is hot, and this is hot, okay? If I divide this plate into 4, and if I assign a thread A, thread B, C, and D, each thread is trying to calculate the heat distribution on this plate. Okay? So one thread is calculating the heat distribution on this one, and this one, and this one, and this one, for a second only. Okay, let's say from T1 to T2 2. Okay, for a second. Okay, so I want each of them to finish their jobs so that I can start running from T2 to T3, okay? So I need this kind of a barrier. Each of them has to finish its job, okay? Each of them has to finish its job. And when they finish their jobs, then I can start running another job, saying that now get T2 and this one. And put another barrier, okay? So each one has to come to the same second at the barrier. So this is a typical application for the barriers. Another synchronization, inter-process communication mechanism. Okay, any questions? If there are no questions, then I am going too slow. I will skip the rest of the inter-process communication part. And let's go back and think a little bit about what we did. Inter-process communication. There are many. I mean, we have been looking at the algorithm, Patterson's algorithm, 1960s, right? I mean, it is still working. People have been working on these kind of problems for a long time. They developed lots of techniques for inter-process communication, and we looked at some of those. But inter-process communication is something very hard. Sometimes, like the language of Java, we get help from the programming language, and most of the time the problems are standard, or the problems you are trying to solve already solved by many different people. So you copy one of the examples and modify them. Still many problems with the deadlocks like that. You see the deadlock here? Everybody is waiting for somebody else and nobody is moving. See, nobody is going, nobody can go that way, nobody can go this way, nobody can go this way. See? But they are all empty, right? There, you can see it. You see that, right? Okay, nobody is going that way or this way or that way. They are all empty, and everybody is waiting for something to happen. This is what happens when you are trying to do inter-process communication, and you are waiting for something else to happen. This is called deadlock, and we will look at this in a more careful way later. Okay, many possible scenes, and depending on environment and underlying or operating system. Okay, if there are no questions, I will start talking about the rest of the chapter 2, which is scheduling. Any questions? Okay, so let's repeat once more. Actually, I wrote it here, somewhere there. At the beginning of the class, I forgot. Yeah, spin locks. We look at the spin locks. We said that they are too inefficient, CPU wasting time. Then we invented the semaphores for non-busy waiting, blocking kernel cores. Then mutexes are a specialized version. Condition variables are used with the mutexes. Then we said that these are too difficult to. Okay, this is inefficient. Okay, these are too difficult, and then we what was the answer for these too difficult thing? Monitors. Monitors came in. We said that we can get help from the operating system. We can get help from the language, programming language for the monitors. Then we said that these are. So what is the problem with all of these, including monitors? So what is the problem with all of these? Spin lock, semaphores, mutexes, condition variables, and monitors?
I want to shade.
What?
Works only in the machine.
Yeah, shared memory. They work with the shared memory. Shared memory. So for these we have message passing. So that's what we did for the last 2 weeks, I guess. So go back and read the book. The discussion is very good. The examples are more detailed. I will not go into the details of those stuff. Instead, I will go back to my slides and let's look at this scheduling. Okay, in time-shared or multi-programming environments, processes or the threads work for a while, then they would block, then they work for a while, then they block, and this is one way of this is an example how a thread works, takes the CPU time, and so for some other processes it is different. Okay, so the process works a little while, then it blocks, then it works for a little while, then blocks. So why it is blocked? Because it needs for an I/O, right? So it needs waiting for I/O. So waiting for I/O. In a CPU bound process. So the CPU is used most of the time. Waiting for I/O takes less time. So it is called a CPU bound process. Okay, the one in A, part A, is CPU bound process. In part B, it is I/O bound process. I/O bound process. So when we are doing the multi-programming, that multi-program means that we have more than one process running in the memory, right? We have one process running in the memory. When we are doing the multi-programming, in these places where the process is blocked because waiting for an I/O, we could run other processes, right? We could run other processes. So the decision of which process to run when one process is blocked is called scheduling, and there are many ways of doing this scheduling, and we will look at those scheduling methods in this rest of the chapter. Okay. Okay. Suppose we have several processes are runnable. Okay, which one is run next? Okay, many different ways to make this decision, and we will look at them one by one. Okay. Remember the batch systems? What was the batch system? Batch system. It was the first examples of operating systems. Batch system. Give me an example of a batch job. Inventory calculations, right? We are doing the same thing over and over, millions of times, like the calculations of the interests for a bank, okay, for each customer, or the payroll printing, okay, payroll calculations. I mean, the Turkish government has, let's say, 600,000 government workers, and you need to calculate their payrolls at the end of the month, right? So somebody has to do it. A computer, a mainframe computer, does this job for you. It's a batch processing job. So in the old batch systems, they didn't have the scheduler. They just read whatever was next on the input tape. Actually, I mean, the scheduler was the person who fed the tape to the system. Okay, who fed the system, who fed the tape to the system. He decides to which batch job runs next. Okay. Later, when we started having time-shade systems or interactive systems, then we had the problem of which process to run next has to